Okay, good morning, everybody. We're going to go ahead and start this final countdown event again. So we have the last 5 remaining final countdown events left until the end of Friday. So with that, I'm going to go ahead and hand it on over to Ernest Hildred, and he's going to be taking over from there. Go ahead, Ernest. Go ahead, Ernest. Ernest, we can't hear your audio.
What about now?
We can hear you now.
Okay. My internet is kind of unstable, it says. So if I lose sound or something, can someone just notify me? So again, I am doing a presentation on exponential functions and logarithmic functions. So exponential functions are represented by a form of standard of f of x equals to b of x, or graphing when you have y equals b to the power of x. So an exponential function has a base of b, and b is a positive constant other than 1, in that the b has to be greater than 0 for it to work. And x is any real number. So we have base and exponential logarithmic forms. So the logarithmic form would be shown as y equals log base b x. And exponential form, we have it as b to the power y equals x. All right, so they have transformations for the graphs that they have. This is a chart that is shown to have the shifting of it or transformations of it. So a vertical translation has the graph of g of x, which is represented with b to the power of x plus c. It shifts the graph upward with C units. So the constant C is the one that makes the graph change, and I shall show you. So we have the graph here. I have it here. So we have okay, so we have the exponential here represented with the power 2 and plus 3. So as we were shown with the previous chart, that if we have a positive, it'll shift it upwards by the amount here. So the last one that we had was 3. And if we subtract 3, it'll move the graph downwards by 3. And you can have a horizontal shift in the exponent. So if we add a number or subtract a number, it'll shift it. So this is the graph. We can so as you can see, the graph shifts downward by 3 units from where it was previously at. So if we were to begin with that, so, and if we do the exponent, so the graphs will change and they will shift. And as you can see, if you change anything to the equation, it'll change with the graphing there. So we have vertical translation, horizontal translation, reflection, vertical stretching or vertical shrinking, and horizontal stretching or shrinking too. So those all will be shown on a graph. So in order for the shifts to happen or the reflections or stretching or shrinking, they have to follow certain things. So in the middle of my chart here, it gives the equation to show how they would change. Usually it is done by addition or subtraction to the equation and also multiplication or the exponents. So for a horizontal translation to happen, the shift would have to be with the constant or the C units and the exponents. So that would have it being going from a large number to a bigger number or smaller. Reflection is shown about the axes, either the X or the Y. So if you have a negative B, that would reflect around the X-axis. And if it's a positive B and a negative X, that would be about the Y-axis. And then you would have the vertical stretching. So vertical stretching is if the C is greater than 1, but for it to shrink, it would have to be between 0 and 1. So it had to be greater than 0, but less than 1. And horizontal stretching or shrinking would have the horizontal shrinking if the graph was greater than 1, and horizontal stretching would be if the graph was, if the number for C is greater than 0 but less than 1. So here I have the graph on chart for a vertical translation. So G of X equals B of X plus C, and the shifts of the graph would be C units. So if we go back to the chart that I had, that we have here, that we have it here like this. So I use this as a way to check my work for some of the logarithms. I know a lot of people have computers now, and I also use a graphing calculator. It's an old one, but it's still reliable. So I use this to check my work and to see how things work out with my functions. So what would happen is you would take the equation that we have here for g of x equals b to the power of x plus c. And as you can see in the chart here, you would put the number that we have for x in the exponent portion. So I usually do about 5 numbers just to show how it would look. And I begin by putting in the number for x, so it's b negative 2. So 2 to the power of negative 2 is 0.5. You add the 3 and it goes along like that. I'm sorry about the signs. They seem to have changed on me, but you would just add 3 and you would continue on and plot them in a graph like this. So this is a vertical translation. It's similar to the one that we saw. This one is G of x equals b to the power of x minus c. So this one you would do the same. For this one, I started plotting. That way you can see how it begins to go from the point that I chose. I chose a negative 2. You place that in for x. So negative 2 for the exponent. We have 2 to the power of negative 2. That gives us 0.25. You subtract 3. That gives us negative 2.75. I plotted that the first point. The second point would be at negative 1. So 2 to the power of negative 1 is going to be 0.5. You subtract 3 and you have negative 2.5. So I plotted that second point. All right, now 2 to the power of 0 minus 3. So anything to the power of 0 will equal 1. So 2 to the power of 0 equals 1. Subtract 3 and you get negative 2. So that's where the third plot is here. So if we go to 0 down to negative 2, 2 to the power 1, subtract 3. So 2 to the power 1 is just 2. and then we have 3. So 2 subtract 3 is -1. That's where I get my 4th point here. And the 5th point is 2 squared 2 and minus 3. So 2 squared is 4, subtract 3, and then it equals 1. So that's the last point. So if you're not too sure of how it's going to continue to look, you can continue on with more points and then check to see how it would look from there. So horizontal translation, the exponent of c added will shift the graph to the left. And the same here, it shifts to the right with the c, so you would subtract. Here is the reflection. You have the base, which is b. It's negative, so it would reflect around the x-axis. And then you would have a negative exponent of x, and that would reflect around the x-axis. All right, so this is a graph that I have for the reflection. So as you can see, this is the normal graph here. But if we were to change it, so now you can see the shift from the original to the next. So as you can see, a positive runs in the red. It goes here. It goes upwards. It goes downwards and then upwards. And this one goes upwards and then downwards for the next one. So this is how it would look if you were to change the base from a positive to a negative, as we had shown in the chart. All right, and now for the exponents. So if you check the exponents, you'll see that that'll change. So this is just if the base changes, but if we do the exponents, we shall see how they change. So this one's positive, and then we'll see how a negative works. So you can see the exponent is a positive 1 on top in red, but then if we change it to negative, then it changes. So that's if it's an odd. So as you can see in the original, that it is a parabola here in red, but then it changes when you change the exponent to being a negative here as it continues up, and then it continues down to the right. And that gives us a reflection about the y-axis. Okay, vertical stretching and vertical shrinking. So we have c times b to x. So that's where it will begin to stretch or shrink. Okay, so we'll have the original on top of x squared, and then we'll do 2 for the next, and to shrink. So in red is our original. This one is as it would be. So when we change the front with a constant that is positive of 2, it causes it to shrink, as it does with the purple graph here. Now, that is because our C is greater than 1. Now, if we were to go between 1 and 0, we would have it to stretch. So we did half. So that makes it in black stretch out. So we can even go further with 0.25. As you can see, it stretches out further. And if our number increases for being higher than 1, let's go with 4, it shrinks even more. So this is what they mean by there's stretching and shrinking of it. So as you can see, our original x squared is here. In red, it hasn't changed, but as you increase it by a constant higher than 1, it shrinks. And with a number between 0 and 1, it stretches out, so it can continue on like that. So as you get lower with the number, it gets wider with the graph. Okay, horizontal stretching. So again, we have the base times or base raised to the constant c and x. So it'll shrink if it's greater than 1, and if it's between 0 and 1, it'll stretch. So if we change this to only the constants, so again, we have b to the c of x here. So we're going to have x, and then we'll have a number next to it. All right, so we have our graphs. So we have 2 to the power of x in red. That's our original graph. Now, like I was saying before, that when we add in the constants that are greater than 1, it will shrink as it did here. With the purple graph, this is our second one. So as you can see, it shrunk inwards. And again, with the number between 0 and 1, it stretches outwards. So again, as the number gets smaller, it'll stretch out, and as the number gets bigger, it'll shrink. So again, I tell students if they're not able to check by hand, they can check on the computer or with a graphing calculator to check their work. That way they know how the graph will look in accordance to how they have it written. So we have some basic log properties. The general ones is that log b is 1 is equal to 0, and then log b and b equals 1, and log base b and power 2 of x will equal to x, and b log and then subscript b x is equal to x, and the logarithm of log 1 is equal to 1. And you can also do this on your calculators. I use an old-fashioned calculator. These are presets, and you can also use your phone if you know how to use your phone's calculator, whatever you're good with. So log base 10 is equal to 1, and then log base 10 raised to the power of x is x, and then 10 log base x is equal to x. And then we get into natural logs. Natural logs are the general properties just with the natural log. So log base b with 1 equal to 0, and then base b equals 1, and then same thing with b to the power of x equals x, and b log base bx is equal to x, and you do the natural log of 1 is equal to 1, and natural log e is equal to 1, and natural log e to the power of x is x, and the same. So these are the basic logarithms. And that's the end of my presentation. Is there any questions?
Okay, thank you, Ernest. Do we have any questions for Ernest?